Hey everybody, Dr. A here, and in this video we're going to be exploring an example of particle equilibrium. So let's go ahead and get started. In the given information, we're being told that a mass m is hanging from point B, and we're being asked to compute the cable forces in terms of that mass m and determine the maximum value of that mass so that no cable develops a tensile force greater than 300 newtons. So let's go ahead and take a look at the figure that we have here. Here we have this mass M that's hanging from point B that's part of this cable system. So if you take a look here, we have 4 cable segments. We have a cable segment from A to B that's at a 30-degree angle. We have a cable segment from B to C that's horizontal. We have a cable segment from C to D that's at a 45-degree angle, and we have a cable segment from C to E that's at a 3-4-5 slope ratio. Now, one of the unique aspects of this kind of problem is that this is really like a 2-step particle equilibrium problem. If you notice, we have more cables than we do in a traditional 1-step particle equilibrium problem, right? So typically we're used to dealing with maybe 2 cables connected at one common particle with a weight or a mass at that particle. Well, here we have 4 cables. So we're going to have to jump from one particle to the next at some point in our process. The next unique aspect of this kind of problem is that we don't actually have the mass value that's hanging from point B. In fact, we're being told to determine the maximum value that this mass could be so that none of the 4 cables will develop a certain tensile force, in this case 300 newtons. So how do we go about a problem like this? Well, we want to take an approach pretty much similar, or in fact the same, as we would with what we're used to before, okay, with what we're accustomed to doing with just 2 cables. So I'm going to go ahead and write solution here, okay? Now, the first thing I'm going to do is we need to, instead of having mass, we need weight, right? Because when we're applying equilibrium equations, we're summing forces up. We don't sum masses up. So the first thing I'm going to do is I'm going to say, well, hey, this mass needs to be converted to a weight by multiplying by what? Well, we want to multiply by the acceleration due to gravity, or g. So we'll say weight equals mg, all right? Now, in this particular problem, which version of g do we use? We use 32.2 feet per second squared, right? Wrong. We do not do that. We use 9.8 meters per second squared. How do I know to use 9.81 meters per second squared instead of 32.2 feet per second squared? Well, if you look in the given information, we're interested in making sure none of the cables develop a tensile force greater than 300 newtons. So because we were told in the problem statement some information about a value in newtons, which is in the SI system, we need to use that as a context clue to say, hey, I'm going to use the SI version of acceleration due to gravity, which is going to be 9.8, or really we're going to use 9.81 meter per second squared. So we can rewrite this as 9.81 meters per second squared times the mass. Now, I'm going to leave off the units for my intermediate calculations just to help me keep track of things a little bit better. But just know that this 9.81, it carries the units of meters per second squared. And this m right here is the m for mass that we don't know right now, okay? So now I've got this weight hanging from B that's equal to 9.81 m, all right? Well, now what we're going to do is we're going to start at a particle where we know something is occurring or something is applied. So we're going to start at particle B because we know that that's where this mass or this weight is hanging, okay? So I'm going to start by saying free body diagram of point B. So I'm going to draw my particle B here, and I've got this weight hanging down here. And remember, that weight is 9.81 times m. M is the mass that we don't know, that we're trying to solve for. Now, what's coming off of this particle FB? Well, I've got an unknown force here. I'm going to call that FBC. I have an other unknown force coming off, pointing to the upper left. That's going to be FAB, okay? And our free body diagram needs to show appropriate angles, so that's at a 30-degree angle. So here we're ready to go ahead and apply our equilibrium equations. And remember, we know that we have two equilibrium equations for forces when we analyze a two-dimensional particle. So what are those? Well, our first equilibrium equation that we can use is sum of the forces in the y direction equals 0, and we call things pointing up positive, okay? And so here, I'm going to say FAB times the sine of that 30-degree angle, and then I'm going to say minus 9.81 times m equals 0. Okay, now that's all I have in this free body diagram that has a vertical or y component. Okay, and so what have I done here? I've set up this equilibrium equation, and the weight that's hanging here is kept in terms of mass m, which is part of what our directions told us to do. Compute the cable forces in terms of mass m, all right? So I can do a little bit of rearranging here, and I can say FAB is just going to be equal to 19.62 times m. Now, if you're wondering where I got 19.62, what I did was I moved the 9.81 m to the other side of the equation, and then I divided by sine of 30 degrees. If you remember from your trigonometry, sine of 30 degrees is 0.5 or 1/2, so you're essentially multiplying 9.81 by 2 when you do that operation. So that's one of my forces. Now I'm going to apply my second equilibrium equation at this particle. That's going to be sum of the forces in the x direction equals 0. Forces pointing to the right are considered positive. And here I'm going to say negative FAB times the cosine of 30 degrees plus FBC equals 0, okay? Now, this negative for FAB, the reason why it's negative is because our cable force FAB is pointing into quadrant 2, which means it's got a negative x component. It's got an x component pointing to the left, and we're saying things pointing to the right are positive. So that's why we have this negative here. Now, do we know FAB? Absolutely. We just solved for that. That was the 19.62 m. So I'm going to say negative 19.62 m times the cosine of 30 degrees plus FBC equals 0. And I can do a little bit of rearranging here and solve for FBC. And when I do that, I'll get FBC equals 16.99 times m. And remember, that m is that unknown mass that's hanging there. So what I've done here is I have applied my equilibrium equations at particle B, and I have solved for the cable force in AB and in BC in terms of that mass m. But I'm not done yet, right? I have two more cables I need to worry about. So what I'm going to do now is move to point C, all right, or particle C. Now, if you notice, particle C is on the opposite side of the same cable BC that we've already handled or dealt with, right? Particle B and particle C are connected by the same cable. So watch what's going to happen here. I'm going to scroll on down a little bit. I'm going to say free body diagram, and I'm going to look at particle C, okay? And so here's my particle C, and I am going to draw a force coming off here pointing to the left. That's going to be FBC, and guess what? This FBC that's pointing to the left of particle C, it's the same FBC that we just solved for. So I can go ahead and write that this is equal to 16.99 m, okay? In fact, let me write that a little bit nicer for us. FBC equals 16.99 m, okay? Now, what else is coming off of particle C? Well, we have an unknown force coming up here. This is going to be FCD, and that's going to be at a 45-degree angle. I'm going to draw that angle in just a second. And then I also have a force CE that is at a slope angle. So let's go ahead and draw these in here. That's 45 degrees. And then FCE, of course, was at that 3, 4 slope. All right. So now what I'm going to do is, now that I'm at a new particle, particle C, I'm going to apply my two force equilibrium equations again, but now at particle C. So I'm going to start with sum of the forces in the y direction equals 0, and we say things pointing up are positive. And so I can say FCD times the sine of that 45-degree angle minus FCE times 3/5 equals 0. And I can't really do anything else with that right now because both FCD and FCE are currently unknown. So then I'm going to go ahead and write my second particle equilibrium equation. Sum of the forces in the x direction equals 0. Things pointing to the right are positive. So here I'm going to have negative 16.99 m plus FCD times the cosine of 45 degrees, and then plus FCE times 4/5 equals 0. All right, so what do I have here? Well, if you notice, here we have two equations. We have this first one from summing forces in the y direction, and we have the second equation from summing forces in the x direction. And these are working simultaneously. This is a system of two equations. And what are our two unknowns in this particular system? FCD and FCE. So for the purposes of solving this particular system of two equations with two unknown forces, everything else is treated as a constant, okay? So here's what I'm going to do. I'm going to say solving these two equations simultaneously gives the following. We'll get FCD equals 10.30 times m, and we'll get FCE equals 12.14 times m. Now you might be looking at this and might be saying, how did I get to those answers so quickly? Well, this is a system of two equations with two unknown values. So there is all kinds of techniques you can use to solve this system of equations. Probably the easiest would be substitution if you were going to do it by hand. Or if you have a TI-36X Pro, you could put this in the system solver and you can end up solving for these constants 10.3 and 12.14. Now, if you put this in your calculator, for example, I use the TI-36X Pro a lot. It won't be able to handle the fact that you have an m incorporated in here. You would only be able to put in the actual constant of 16.99, not the m. But that's okay. You'll solve it. You'll get 10.3 and 12.14. You'll just have to remember that it's actually 10.3 times m and 12.14 times m, and write that down on your paper. Okay. So if we were going to summarize our forces in terms of m, we would have FAB equals 19.62 m. We would have FBC equals 16.99 m. We would have FCD equals 10.30 m. And then we have FCE equals 12.14 m, and these are all, of course, reported to 4 sig figs. Now, here's what I want you to be careful about. Remember, I've said it 4 or 5 times now, but this m is the unknown mass. It's not meters, okay? Don't get confused. We're not talking about m in meters. We're talking about m as the unknown mass that was hanging from particle B, okay? Now, also, I want you to remember that all of these coefficients, these numerical coefficients, 19.62, 16.99, 10.3, and 12.14, all have units of meters per second squared. We mentioned that earlier, okay? So all these coefficients have units of meters per second squared, and we know that because they all came from manipulating that 9.81 meters per second squared from the very beginning, from the first step, okay? So so what do we do next? Well, I'm going to change colors here, and let's go ahead and solve the rest of the problem. The maximum force the system can sustain is based on the largest coefficient of the cable forces, okay? So what that means is, of these four cables, cable AB will always have or carry the largest force because it has the largest coefficient. So let's make a note here, okay? I'm going to say will carry largest force. And again, we know that because it has the largest coefficient of all four of these cables. So to answer the last part of this problem, this question, what we're going to do is we're going to set the force in AB, okay, which is, what do we say it was, 19.62, and we got meters per second squared times M equal to 300 newtons. Remember, in the problem statement, the 300 newtons is the largest force that any of the cables can support based on the directions, okay? And we want to solve for the mass that will prevent any force developing in the cables larger than 300 newtons. So we use FAB because that's the largest cable force that will develop, and we set that equal to 300 newtons, okay? And what we can do is we can say M equals 15.3 kilograms. And that is our answer. Now, what I did there was I looked at this portion of the equation and I solved for this M. So I said 300 divided by 19.62. Now you might be wondering, where did the kilograms come from? Okay, well, let's do a unit check real quick so we know where it came from, okay? Unit check. So what is a newton? 1 newton is equal to 1 kilogram times meters over second squared, okay? So that is something you should know from basic physics or even physical science, all right? And so if I say 1 newton is 1 kilogram meter per second squared, then what I'm really doing when I'm manipulating these units is I'm saying a kilogram times meter per second squared, and I'm saying that's divided by meters per second squared, right? Because I'm dividing a newton, which is a kilogram meter per second squared, by 19.62 meters per second squared. This meters per second squared will get put into the denominator of that fraction, okay? And so if I do a little bit of rearranging here, remember this is just fraction manipulations, I've got kilogram meter per second squared times second squared over meters, because we have a fraction in the denominator of a bigger fraction. And we see that the seconds cancel and the meters cancel, and you're left with a number that just has units of kilograms, and that's what we have here that we wrote there, okay? So hopefully you found this example helpful. If you did, please hit like and subscribe, and be on the lookout for other content similar to this. Thanks for watching.